So in the last class, yeah, in the last class, we were discussing the source follower and how to find the frequency response of a source follower. So I will just revise it and then we will continue. So as you know that a source follower is something which follows a source. That is, output will always taken from the source and input will be provided to the gate. Okay. So here you can see that the output V naught is taken from the source terminal across the load resistance, and input V signal is given to the gate terminal through the resistance called R sig. Meanwhile, the drain will be always grounded because drain is common to both input and output. So it will be grounded whenever high frequency response is considered. So please aware about that particular fact in a source follower. Whenever you are going for a frequency response analysis, the drain has to be grounded and we will take the output from the source and input to the gate. Okay. And by using time constant open circuit time constant method, we are going to find the cutoff frequency FH. So for that, we have to consider the capacitances one by one. And what are the three capacitances we have? We have CGD, we have CGS, as well as CL. CGD is a capacitance connected between the gate and drain. CGS is between gate and source, and CL is a load capacitor connected at the source. Unlike the previous configuration, CG or CD, here the load capacitance is connected to the source. Why? Because this is a source follower, right? Whereas in common gate and common source, we have connected this at the drain. Okay, this is a source follower, so that the output is taken across a source. That is why the load capacitor is connected across the source terminal. And we are considering the body effect. Because of the body effect, I need to consider two current sources. Okay. So in typical configuration, wherever we are not considering the body effect, in that case, the signal current will be expressed as GM into VGS. But here, since body effect is predominant, we need to consider GM-VGS as well as GMB-VBS. Okay, this is nothing but the current due to the body effect, because we are having a separate terminal body which is grounded, because of which we have a voltage called VBS, and there will be a current component because of this transconductance and voltage. That is what is called as GMB into VBS. So we have two currents flowing from drain and source. Then there is a resistance called R0, which is nothing but your internal output resistance that is available between the drain and source. So this is the frequency response, the equivalent circuit of a source follower. Source follower is otherwise called as common drain. Then what we have done, we have simplified this particular diagram and we have redrawn this. Already we have discussed this yesterday. So let me tell you how you have redrawn this particular circuit. So what I have done is, since drain is already at the ground, right? This terminal is at ground. So rather than connecting this in the horizontal path, what I have done is I have disconnected the CGD. Okay, I have disconnected the CGD and I have connected it between gate and ground in a vertical manner like this. Both are same because drain is at ground. Okay, so rather than connecting in this particular position, I'm connecting it in a vertical way. Okay, between the drain and ground terminal. Now another modification that you can see is I have eliminated this GMB VBS. Okay, so whenever a current source is eliminating or removing, what you need to do, you need to replace it with a resistance, and the resistance value should be equal to the reciprocal of the transconductance. So what is the reciprocal of this transconductance? It is nothing but 1 by GMB. Okay, so if I'm removing this current source, I will have a resistance 1 by GMB in parallel with R0. Okay, so as of now, what and all resistance that we have across the ground and that source terminal, we will have R0, right? Then RL is also between the source and ground. You can see RL is between source and ground. R0 is also between source and ground. So in the place of this current source, we are having 1 by GMB as a resistance, because I'm eliminating this current source and I'm replacing it with a fixed resistance. Already you have learned it in the T equivalent circuit. In the T equivalent circuit, whenever you are replacing a current source, you have to replace it with a resistance equal to the reciprocal of the transconductance. So after seeing this diagram, it is obvious that we are having three resistances connected parallel to each other across the source and ground, and the three resistance are, one is RL, another one is R0, and another one is nothing but the resistance of this current source, that is nothing but 1 by GMB. So these three resistance can be now put together as RL dash, okay, which is connected between source and ground. So RL dash is RL parallel, R0 parallel 1 by GMB. Okay. And this is the current source GMVGS, which is flowing from the drain to source. So this is a simplified equivalent diagram of this equivalent diagram. Already you have done this yesterday. Now let us discuss how to find the time constants. You know the procedure. We are going to find the cutoff frequency of this source follower. In order to find the cutoff frequency, you need to find the individual time constants, and all the time constants should be added together so that you can find a tau h, and further by making use of the equation we will be able to find fh. So first let me consider the capacitance called CGD. So if I consider CGD and open the two terminals and looking into this terminal, the resistance that you will obtain after looking into CGD is Rsig, right? So how you will find this resistance? You need to consider that resistance which is connected across the same terminal where CGD is being connected. Okay, please focus on CGD where it is connected. CGD is connected between drain and ground, right? CGD is connected between drain. This is drain. Sorry, this is gate, right? CGD is connected between gate and ground, isn't it? Before it was here only, but since this is ground, this is also ground, I have connected here. Okay, so CGD is connected between gate and ground. Now, if you look into this terminal, right, which resistance you are seeing? You are seeing Rsig, which is connected between gate and ground, because whenever you are finding the equivalent resistance, I need to short circuit my voltage source. So if you short circuit this voltage source, you can see that the resistance Rsig is connected in the same terminal, across the same terminal where I have connected CGD, right? Therefore, the equivalent resistance that you are getting after looking into the terminals of CGD is nothing but your Rsig. Is that clear for you, students? Any doubts in that? What you will do, you can write the expression RGD equal to Rsig, where RGD is the resistance obtained after looking through CGD. After writing RGD, now you can write the time constant. Time constant is nothing but the product of the resistance and the particular capacitance what you have considered. You have considered CGD now, so replace RGD as Rsig, multiply it, that will be equation number 1. Coming to the second case, that is CL. If you remove the CL and open it, the resistance that you are getting is RL dash, isn't it? RL dash. So directly you can write RCL is equal to RL dash. RCL is the equivalent resistance that you are seeing through the CL, the capacitance CL. And RL dash expression already we know it is the effective of, cumulative effect of the three parallel resistances RL, R0 and 1 by GMB. This is your general equation. Now, if at all, if there is no transconductance, if at all there is no transconductance, don't do this. Okay. If at all there is no transconductance considered, right? This is the body effect. If there is no body effect considered, I can remove this so that I will retain only this RL parallel R0. Then you need to multiply with CL so that you will get the time constant tau CL. So tau CL is the product of the effective resistance that you have considered into the capacitance CL. You can go with this equation, but this is a special case where there is no body effect. You know what is body effect? Body effect means the body will be separated from the the source terminal, and it will be grounded. Normally, the body will be tied to the source. Otherwise, if there is body effect, means the body should have been grounded separately rather than connecting with the source. So in that case, you have to consider the effect of 1 by GMB as well. So now we have found the two time constants. Now coming to the third case, that is CGS. I think we have stopped yesterday till here, right? Now coming to case 3. that is CGS. We have one more capacitance called CGS. Yeah. If you see CGS, CGS is connected between gate and source. CGS is connected between gate and this is gate. Okay. Gate and source. Now, if you look through the CGS, you can't see any physical resistors connected across the same terminal. So with direct observation, we will not be able to write the equation for RGS, right? RGS is the equivalent resistance that you have obtained after looking through that particular capacitor terminal. But unfortunately, here we can't find any resistance available across the terminals G and S. This is gate. You can mark it as G, D, and S. So what you will do is, if you're not able to see any resistance, means we have to fix a test voltage source or a dummy voltage source Vx. Okay, so I will fix a dummy voltage source Vx across G and S after removing the capacitance. I need to open this capacitance and I will fix the Vx. At the same time, the remaining capacitance will also be removed. CGD and CL, it will not come into the picture at all. Okay, so all the remaining capacitance CGD and CL will be equal to 0. And in the place of CGS, I will fix a dummy voltage source called Vx and I will mark the current Ix. Okay, the current which is coming from Vx can be written as Ix. And meanwhile, the other voltage source V6 should be short circuited. I will not consider this because right now I am interested in finding this resistance across GS. So I will not consider any other voltage. Okay, so the voltage sources has to be short circuited so that R6 will be directly grounded. So this is the equivalent circuit that you are obtaining while considering CGS into our account. Okay, so what I have done is I have connected a voltage source Vs across the gate and source. Now draw this particular diagram. Okay. Now, in order to find the ratio between Vx and Ix, why we are finding the ratio between Vx and Ix? Because it is nothing but the resistance according to the Ohm's law. V by I is the resistance. So if you can find Vx by Ix, that will be the resistance between G and S. So we can go for RGS. After finding RGS, multiply with the CGS, so you will get tau G. So let us do that. So for that, what we will do is we are going to apply Kirchhoff's current law or the nodal analysis at the source node. Okay. Now, if you see this source node, which is entering current to this node, which is entering current to this node, entering current is, you can see the arrow mark, right? Current will be always entering to the source from drain. Any confusion in that? Current flow through the MOSFET is always from drain to source. So the entering current is here is GM/VGS, right? Equal to, what about the leaving current? What about the leaving current? Here, the current is leaving in this direction, Ix, right? Because here is positive. So I have to mark the current flow in this direction. So that is leaving current. So Ix. Okay, Ix minus V0 divided by RL. You can see that the load current is nothing but the voltage divided by resistance. Okay, load current can be expressed as the load voltage because you are taking the output across the source. So the voltage will be V0. Output voltage can be represented as V0 divided by the resistance RL dash. That will be the current passing through the load resistance and it will be minus. Okay, the polarity of the source follower like this, it will be like this. Okay, since the current is moving in this particular way, I should keep this voltage as negative. So minus V0 divided by RL dash. So this is the equation that I'm getting after applying the nodal equation. Any confusion in this? This is the entering current, and one current is leaving through RL, and another current will be leaving through what? Leaving through the RSIG. This is considered as IX. Now, what will be the voltage across VGS? Voltage across VGS as of now, it is Vx. Right? So rather than putting GM VGS, now I can put GM Vx. Because across G and S, we are having X, Vx. Therefore, this equation VGS can be replaced as Vx. So the equation will now become GMVx is equal to Ix minus V0 by RL dash. That's equation number 8 or 1, whatever it may be. So this is the equation that you got after applying the nodal analysis at the source. Okay. Now you tell me in this equation, which is the unwanted term. Please remember that you need to find the ratio between Vx and Ix. But if you see equation number A, what is the unwanted term? With this equation, will you be able to calculate the ratio between Vx and Ix? If not, why? Which is an unwanted term that you need to replace?
V0, sir.
V0, very good. So we have to replace V0 in terms of Vx or Ix so that I can substitute V0 and take Ix common or Vx common, and we will be able to find the ratio. So for that, I need to go for some other equation. So what we will do is, I'll be considering the input mesh, okay, the loop analysis, the input mesh. This is your input circuit. This is the input circuit that we have. So through this mesh, I will be applying the KVL and I will write the KVL equation. So let us do the KVL equation in input mesh. Okay. So I'll start from here. I'll start from this point. Okay. And I will be moving in this direction according to Ix. Because Ix is moving in this way, right? So I will also move in that direction. So plus to minus, it will be negative. The drop is, what is the drop across RSIG? It is Ix into RSIG. So the equation is minus Ix into RSIG, right? Minus Ix into RSIG will be the drop across RSIG. After that, I have to come here. Here I have to come. What will be the voltage across RL dash? It is V0. V0 is the voltage across RL dash. Plus to minus will become minus. If I'm moving from plus to minus, I have to put the symbol negative. If I'm moving from negative to positive, I have to put a symbol positive. Okay. So this is plus to minus. So it will be negative. Coming through in this direction. Plus to minus. Again, it is negative. Again, minus to plus. So this will be positive Vx. So based on that concept, I can write my equation as follows. I hope you understood. Already you have studied these things in third semester, how to apply KVL, right? So you can go through the direction of Ix, then see the polarity. Accordingly, you need to put negative and positive symbol. If you are moving from positive to negative polarity, you have to put negative sign. If you are moving from negative to positive, you have to put positive symbol. Then algebraic sum of all the voltages across a closed network will be 0. That is nothing but your cross voltage law or mesh analysis. So that equation I have written here. That is minus Ix into R6 minus V0 plus Vx is equal to 0. Now, if you rearrange this equation, I can take this V0 to the right hand side. So V0 will become Vx minus Ix R6. So this is the equation that we actually wanted, because I can replace my V0 in terms of Vx and Ix. Equation number 8. So put B in A. Put B in A. And rearrange Vx and Ix. And find the ratio between Vx and Ix. So GMVx is equal to Ix minus, in place of V0, we can put Vx minus Ix into Rsig. In place of V0, I have put Vx minus Ix into Rsig divided by RL dash. In that way, equation number A has been rewritten. Open the brackets and take all the terms consisting Vx to the left hand side and retain the Ix terms in the right hand side, so that we can find the ratio between Vx and Ix after taking the common factors. Please do it. Simple max. Now you can take LCM here. Vx by Ix means it is 1 plus Rsig by RL dash divided by 1 by RL dash plus GM. After that, you can take LCM, right? So RL dash will be common for both the denominators. I mean, for both numerator and denominator. So that will be cancelled. So the equation will become RL dash plus Rsig divided by 1 plus GM RL dash. So this can be considered as the ratio between Vx by X, that is nothing but Rx, which is equivalent to RGS, because Rx is a resistance that is available between the gate and source. So I will take it as RGS. So please remember that whenever you are not able to find any physical resistance directly across the respective terminals, then what you will do, you will connect a dummy voltage source. From that, create a current flow. After applying the nodal analysis or mesh analysis in the respective nodes, form two equations, solve it. The ratio between Vx and Ix is nothing but the resistance across that particular terminal. So that is a concept that you need to understand. So once you find RGS, multiply with the capacitance CGS. So that will be your tau GS. This is a result of case 3. Now add all the three equations together. Add all the three equations together. That tau G, case 1, case 2, and case 3. Tau GD, tau GS, and tau CL. So this is the expression that we got, that is tau H is equal to the first equation CGD Rsig plus CL RL dash plus CGS into RL dash plus Rsig by 1 plus GM into RL dash. And you know what is RL dash? RL dash is the parallel combination of the three resistances, that is RL, R0, and 1 by GMB. And once you get tau H, by making use of our final expression 1 by 2 pi tau H, we will freeze our FH. Okay, so this is the results that we have obtained from this particular analysis. So write down the results: RGD, RGS, RL dash, RCL, tau H, and FH. Because you need to remember this for numericals. So start writing all the final result of this particular derivation in a box so that it will be easier to remember. You need to do this for all the three configurations: common source, common gate, and source follower, otherwise called as common drain. So the results are: first, RGD equal to Rsig, RGS is equal to, just now we have learned how to find RGS, that is RL dash plus Rsig divided by 1 plus GM RL dash. Then RL dash is equal to the parallel combination of the three resistances. Finally, RCL equal to RL dash, tau H and FH. So start writing the results, then we will continue. Done. So if you have completed the results of the previous analysis of drain follower, source follower, now we can go with this problem. Let's take down this numerical problem. Consider a source follower specified as follows. W by L. W by L is the aspect ratio of the transistor, where W is the width of the channel and L is the length of the channel. So that will be 7.2 micrometer divided by 0.36 micrometer. ID is equal to 100 microampere. GM is 1.25 milliampere per volt. Chi equal to 0.2. So if chi is given, means it is understood that we have to go for GMB. That is the body effect. So I have to consider 1 by GMB in our equation for finding RL dash. Clear? Otherwise, if nothing is mentioned regarding chi or body effect, I will remove this 1 by GMB and I will stick on with RL parallel RC. Is that clear, students? So whenever the value of chi is given in the question, you should go with 1 by GMB also while considering the RL dash value. Clear, Sriraj? Then we have R0 20 kilo ohm, R6 20 kilo ohm, RL 10 kilo ohm. So all the resistance is being given, then followed by the three capacitances. So we have three capacitance. It is understood that we need to find all the three time constants related to tau GS, tau GD, tau CL. Then we will find the overall time constant and later we will find the cutoff frequency. So first, let us find what is RL dash, because in the circuit analysis, we have taken the concept of RL dash, that is nothing but the parallel effect of capital RL, R0 and 1 by GMB. For simplification, we have done like that, right? We have three resistances in fact, but together we have treated it as RL dash. So let us find the value of RL dash first. What is RL? RL is 10K. No need to convert into ohms. So let it be in kilo ohm itself. So 10K parallel, R0 is 20, 10 parallel 20, parallel 1 by GMB. What is GMB? Yes, what is the expression for GMB? What is the expression for GMB? In the last class also, we have done the same problem using GMB. How it will relate with the GM? Soumya? What is the relationship between GMB and GM? Yes, chi into GM. Very good. So chi is 0.2 here. So take that 0.2 into GM. GM is 1.25 milliampere per volt. So retain it as milliampere itself. Why? Because we are expecting my resistance in kilo ohm. So let it be in milliampere itself. So 0.2 into 1.25. So first you will do this 10 parallel 20. All of you do 10 parallel 20, get the answer of that, then you proceed with the next value. Don't go for R1 into R2 into R3 by, that is wrong. First find R1 parallel, RL parallel R0. So 10 into 20 by 10 plus 20. That answer parallel 1 by 0.2 into 1.25. Yes, what is 10 parallel 20, students?
20 by 3, sir.
Okay, so 20 by 3 parallel. The other one is
4, sir.
okay. Okay, so 20 by 3 parallel 4. 20 by 3 is 6.66. So 6.66 parallel 4. So 6.66 into 4 divided by 6.66 plus 4. So it will come around 2.5. So RL dash is 2.5 kilo ohm. Now we will start with tau GD. To find tau GD, we have to find RGD because tau is nothing but the product of R and C. So let us see the result. What is RGD? RGD is equal to RSig. So what is RSig here? RSig is given as 20. So directly you can write RGD as 20. Then multiply with the CGD. CGD is 5 femtofarad. So 20 kilo ohm means 20 into 10 to the power 3. And 5 femtofarad means 5 into 10 to the power minus 15. Femto, convert femto into farad. It is into 10 to the power minus 15. So 20 into 5 is 100. 10 to the power minus 15 and 10 to the power 3 will become 10 to the power minus 12 seconds. So 10 to the power minus 12 is nothing but picoseconds. So answer is 100 picoseconds. Now we will go with the second question, tau CL. To find tau CL, we need to find RCL. So what is RCL? According to our analysis, RCL is simply RL dash. So whatever we got the answer for RL dash, that will be taken for RCL also. Now multiply those RCL with the respective capacitor CL. CL is 15 femtofarad. So 15 into 10 to the power minus 15 into the resistance value 2.5 into 10 to the power 3. Again, it will be in picoseconds because 10 to the power minus 15 plus 3, it will be 10 to the power minus 12. So the answer will be in pico. 15 into 2.5 is 37.5, I guess, right?
Yes, sir.
Now all of you do the third term, which is the third question, tau GS. So for that, I need to get RGS equation. RGS equation, we have got that derivation using Vx and Ix, the dummy voltage source and current source. So take this equation, substitute all the terms and let me know what is RGS. Then we will find tau gs. So put your answers in the chat box. RGS value. You need to take this equation. Take this equation and substitute the value of RL dash, R6 GM. Again RL dash. Okay.
5.45, sir.
Good. Answer is 5.45 kilo ohm. Then multiply it with CGS. CGS is 20 femtofarad in our question. CGS is 20 femtofarad. So multiply it with the 20 femtofarad. So 20 into 5.45 is 109. Just check it. 20 into 5.45 is, yes, 109. Again, minus 15 plus 3 will become minus 12. That is pico. So if you see all the three results all are in picoseconds, so you can simply add the three time constants to find the answer for your fourth question, that is tau h. So this meeting will get end now. Rejoin with the same link again. So tau gs plus tau gd plus tau cl together, it will become 246.5 picoseconds. After that, by making use of this equation, we can find the cutoff frequency. 1 by 2 pi into tau h. So 1 by 2 pi multiplied